Before the last curtain fell on World War II, the engineers of the Third Reich had already built things that would take decades for the world to comprehend. From the shores of the Baltic, Werner von Braun launched the V-2, a shell that fell on London at supersonic speed before the warning alarm sounded. The Messerschmitt 262 was crossing Allied bomber formations at a speed that no gunner could keep up with his turrets. The Jagdpanther destroyed 3 Shermans in 40 seconds from positions that no one could locate, with a cannon capable of piercing Soviet armor 2 kilometers away. These achievements did not arise by chance. Behind them operated an unprecedented machinery of war engineering, driven by desperation, by genius, and in many cases by the ideological madness of a regime that confused monumentality with victory. On July 18, 1944, Lieutenant Richard Leonard of the U.S. 8th Air Force wrote a combat report with a phrase that intelligence analysts in Bushy Park underlined before raising it to their superiors. It described an aircraft that had crossed the B-17 formation at a speed that none of the gunners had been able to keep up with their turrets. There was no time to react. The object simply appeared in the German sky and then disappeared. What Leonard was describing was the Me-262, and its origin was not in 1944, but in January 1939, when the Messerschmitt Company received from the Reichsluftfahrtministerium, the Reich Ministry of Aviation, known as RLM, a specification for an experimental jet propulsion fighter. Engineers Woldemar Voigt and Ludwig Bolkow led the design of the airframe, while the engines were developed in parallel at Junkers under the direction of Anselm Franz. The problem was that the engines required materials that Germany could not obtain in sufficient quantity. The turbine blades of the Jumo 004, the parts that rotated inside the engine at 800 degrees Celsius, needed nickel-chromium alloys. The Allied blockade had turned these metals into permanent shortages. France found an engineering solution, an air film cooling system that cooled the vanes by internal currents and allowed the use of lower quality materials. It worked, but at a cost. Each engine lasted a mere 25 hours before needing a complete overhaul. Each Me-262 in active service consumed 2 engine overhauls for every 50 hours of flight. It was a huge technical problem. The political problem was even more devastating. On May 23, 1943, in Berchtesgaden, Hitler questioned General Erhard Milch about whether the Me-262 could carry bombs. Milch replied that he did, without foreseeing what would come next. Hitler, obsessed since the failure to contain the Allied landings in Normandy with the idea of a high-speed bomber that would destroy the beachheads before they could be consolidated, ordered the Me-262 to be converted into what he called the Blitz bomber, the lightning bomber. The decision was technically absurd on 3 different levels. The aircraft had no bombing aiming system. Their engines responded dangerously slowly to changes in power during evasive maneuvers, making each bombing sortie an added risk. And the bomb load reduced its speed advantage to the point of almost eliminating it, which was the only reason for the aircraft in combat. General Adolf Galland, Inspector General of Luftwaffe fighters, directly confronted Goering and then Hitler himself. He explained all this to him with the data in hand. They explained to him, without much tact, that his objections would not be considered. The months that followed, from mid-1943 to late 1944, were lost in forced conversions, failed tests, and technical reversals. Those months represented the difference between a weapon that could have upset the air balance over central Germany and one that arrived when that balance was already irreversible. When Jagdgeschwader 7, under the command of Major Theodor Weissenberger, began interception operations in November 1944, the combat results confirmed everything Galland had argued. JG-7 destroyed more than 400 confirmed Allied aircraft. The elite Jagdverband 44 unit, which Galland himself finally managed to organize with the best pilots available, and which saw combat in February 1945, was racking up victories at a rate that no conventional fighter unit could match. But compared to the 9,000 Allied aircraft operating over Germany in those last months, not even 300 Me-262s operational at their best could reverse the tide. The margin of tactical superiority was real. The scale of the strategic imbalance was greater. The Allies, meanwhile, did not wait passively. General Karl Spaatz, commander of strategic air forces in Europe, authorized in October 1944 specific patrols over the airfields where the Me-262 operated. The pilots learned two specific vulnerabilities of the new aircraft. First, turbojet engines needed several seconds of starting time before responding with full power. Second, during takeoff and landing, with engines at minimum and the plane 200 meters above the ground, it was as vulnerable as any other. Lieutenant Colonel James Selman of the 357th Fighter Group shot down the first confirmed Me-262 in low flight over the Lechfeld runway on August 26, 1944, attacking the aircraft as it touched down. Then came the systematic tactic, not intercepting in flight, where it was impossible to reach it, but at the moment of greatest fragility, in the seconds of takeoff and landing. Of the 1,433 units produced, which included the Schwalbe fighter, the Sturmvogel bomber, the Nachtjäger night fighter, and a reconnaissance variant, fewer than 300 were operational simultaneously at any one time. J-2 fuel was scarce. Pilots trained in turbojets, even more scarce. The runways, a permanent target of Allied aviation. At the end of the war, Allied technical intelligence teams competed with real urgency for captured specimens. What they found in German hangars directly informed the development of the North American F-86 Sabre and the Soviet MiG-15, the two fighters that would fight over Korea 5 years later. The swept wings of the Me-262 and the beginnings of the Jumo 004 became the foundations of post-war military aviation. The Me-262 did not win the war for Germany, but he defined the technical terms of the next one. At 11:34 a.m. on August 2, 1944, the radar sergeant at Chainholme Station at Pevensey on the Sussex coast recorded unusual contact. Estimated speed 740 kilometers per hour, altitude 9,000 meters, heading into the interior of England. In the next 14 minutes, 3 Spitfire Mark 14, the fastest fighters in active service in the RAF, were vectored into contact. None could get closer than 2 kilometers from the target. The intruder tacked over Southampton and returned to the mainland without being intercepted. The Arado 234 was the embodiment of an idea that the Luftwaffe had pursued since 1940, a reconnaissance aircraft operating above the speed of any enemy interceptor. Walter Blum's design team at Arado Flugzeugwerke in Brandenburg-Neuendorf received the original specification in April of that year and responded with a design of remarkable aerodynamic purity for the time. The fuselage was a tube with an almost circular section, with a glazed cockpit in the nose that gave the pilot all-round visibility in all directions. 2 Junkers Jumo 004B engines hung under thin-profile wings. There was no defensive weaponry of any kind. Speed was the only defense, and given the performance of the aircraft, it proved to be sufficient. Early prototypes used a system where the takeoff gear was abandoned on the runway while landing was done on 3 retractable skids under the fuselage. This solution eliminated the weight of the conventional landing gear, but created an insurmountable operational problem. The aircraft was immobilized after landing, unable to move under its own power to the runway. The V5 to V8 prototypes adopted the standard tricycle retractable gear, with which the R234 eventually went into production as a B model. The Versuchsverband Ober der Luft, an experimental unit under the direct control of the Luftwaffe High Command, received the first operational AR-234B1S in July 1944. The reconnaissance flights that followed covered the ports of the English Channel, the Allied installations in Normandy, and the lines of communication in France. The photographs arrived at German intelligence centers with a regularity that no Allied defense system could interrupt. The photo interpreters at RAF Intelligence Command knew exactly what that meant. Germany could still accurately see everything the Allies were doing on the ground, and there was no way to prevent it as long as that aircraft existed. The bombing variant, the AR-234B2, added a new dimension to the problem. The bombing system used an autopilot-assisted Lotfe 7K sight. On approach to the target, the pilot activated the autopilot, which maintained a stable course and altitude, and physically moved towards the site located in the glass nose of the aircraft. From there, he calculated the firing solution, activated the release and regained manual control before starting the evasion maneuver. It was a procedure that required practice and considerable serenity under anti-aircraft fire, but in the hands of trained pilots, it provided reasonable accuracy for an aircraft that no enemy interceptor could reach. The most dramatic episode of the R-234 in combat was the campaign against the Remagen Bridge in March 1945. On March 7th, the US Army's 9th Armored Division captured the Ludendorff Bridge over the Rhine before German engineers could blow it up. It was a catastrophe for the German command. The only crossing of the Rhine that remained intact could become a bridgehead that would open the way into the interior of the Reich without natural obstacles. A 234 B-2 units of 9 KG-76 executed bombing missions against the structure. The Allied anti-aircraft concentration in the area was the densest on the entire Western Front. The R-234s repeatedly tore through it, dropping 500-kilogram bombs that damaged the structure but did not destroy it. The bridge collapsed on March 17th, 10 days after its capture, due to its own accumulated structural tensions. The 210 units produced were studied in detail by the Allied technical teams that captured examples at the Norwegian base in Stavanger and at northern German airfields. Its design principles, clean aerodynamics, the arrangement of engines under the wings, the cockpit integrated into the nose, influenced the jet bomber programs of several countries over the next decade. On November 5, 1942, over the Caucasus, a 20-year-old pilot named Erich Hartmann shot down his first Soviet plane. He was driving a Bf-109. The tactic he used that day was the same one he would use in the 352 confirmed victories that followed, all of them in the same basic type of aircraft, making him the fighter pilot with the most verified kills in military history. The tactic was simple in its description and extremely difficult in its execution. Approach from the rear and upper blind spot of the adversary, close to the distance where it was impossible to miss, burst of less than 2 seconds and escape maneuver before the target could react. Hartmann said that you had to see the target completely fill the scope before shooting. The Bf-109 was designed by Willy Messerschmitt and his team in response to the 1934 RLM-702 technical specification, which called for a modern fighter to replace the Heinkel He-51 biplane with which the newly reconstituted Luftwaffe operated. The design philosophy was radical by the standards of German military aviation at the time, the lowest possible weight and the maximum use of engine power. The fuselage was of minimal cross-section, barely enough for the pilot, engine and fuel. The wing was small, requiring high-efficiency flaps to maintain manageable approach speeds on land. The prototype's Jumo 210 engine was replaced by the Daimler-Benz DB601 in the E version, which saw combat with the Condor Legion in Spain in 1938 and then in the Polish campaign in September 1939. The Battle of Britain in the summer of 1940 simultaneously showed the virtues and limits of the aircraft. The DB601's direct fuel injection provided a concrete tactical advantage. In negative dive maneuvers, when the aircraft pushed the nose down hard, the Bf-109's engine continued to run without interruption, while British Spitfire and Hurricane with conventional carburetors lost power for a few critical seconds. The German pilot could escape with a simple forward thrust of the nose, that the English could not immediately follow, but the range of the Bf-109E was a mere 660 kilometers, insufficient to provide prolonged escort over southern England. The pilots arrived on the English coast with limited time before having to return for fuel and were aware at all times of the counter that was running against them. The Bf-109F, introduced in 1941, was the version that many veteran pilots considered the most balanced of the entire series. With a deep aerodynamic overhaul and the improved DB601E, the Friedrich reached 623 kilometers per hour and combined speed, agility and firepower in a ratio that those pilots consistently described as perfect. The G version, the Gustav, was the most produced, with more than 24,000 units built. To compensate for the opponent's improvements, he incorporated the GM1 nitrous oxide injector to maintain performance at altitudes above 8,000 meters and the MW50 water-methanol mixture injection to obtain extra power in the critical seconds of combat. Each improvement added weight and complexity, and the Gustav inherited and amplified the original design problem that cost the Luftwaffe the most lives from 1943 onwards. The Bf-109's landing gear had a track of just 2.05 meters, the distance between the two wheels on the ground, with a steep heel angle that made the aircraft unstable during takeoff and landing. From 1943, German fighter squadrons were filled with young pilots with drastically cut training programs to compensate for losses from the front. The instructors of the Jagdschulen, the hunting schools, documented with increasing alarm the takeoff and landing accidents that disabled planes and pilots who never got to see the adversary. The Bf-109 served in all German theaters of operations, from the fjords of Norway to the Libyan desert, and fought until the last day of the war with pilots who knew it from Spain in 1937 and with pilots who had never flown anything else. In October 1943, Lieutenant Don Gentile of the USAAF's 336th Fighter Squadron, one of the most decorated aces on the European front, wrote a direct evaluation of the FW-190 for the 8th Air Force Tactical Manual. The central phrase was this: when an FW-190 decides to attack and has the position, there is no maneuver that will stop it. You have to avoid the position from the beginning. The first appearance of the FW-190 on the Western Front in September 1941 produced an effect that few technological innovations achieve in war: complete strategic surprise. The RAF, with the Spitfire Mark V as its mainline aircraft, had at that time nothing that could match the new German fighter in horizontal speed, dive speed, roll speed or firepower. British fighter commanders forwarded urgent reports to the Air Ministry. The answer was that the RAF would not be able to match the FW-190 until the Spitfire Mark IX with the Merlin 61 engine was available in quantity, and that would take almost a year. Kurt Tank, the chief designer of Focke-Wulf, had made a decision that set him apart from all other German fighter designers. He chose the BMW 801 radial engine when the general trend preferred inline engines. The choice was deliberate and defended with concrete arguments. Radials were more resistant to combat impacts because their cylinders, distributed in a circle around the crankshaft, could lose some and continue to function. They were simpler to maintain in the field because they didn't need the liquid cooling system that made the Bf-109 vulnerable to minor damage. Engine management was the FW-190's great ergonomic innovation. An electromechanical device called the Commando Jarret automatically adjusted the fuel mixture, turbocharger pressure, and pitch of the propeller blades based on the throttle position. The pilot moved the throttle lever and the system did the rest. In a combat where the pilots of the Bf-109 had to manage several technical parameters simultaneously under extreme pressure, those of the FW-190 could concentrate exclusively on flight tactics. Tank had designed a relationship between pilot and machine that post-war aeronautical ergonomics would take years to systematically match. The armament was the other main differentiator. The A8 variant, the most produced of the series, with more than 6,500 built-mounted 420mm MG 151/20 cannons, two 7.92mm machine guns in the nose, and two additional 20mm cannons under the outer wings. 6 muzzles in total. The Jagdwaffe analysis determined that 3 seconds of focused fire with the full armament of the A8 was enough to destroy a B-17 Flying Fortress with high probability. The FW-190 became the main instrument of the Reich's defense against USAAF bombing, with Sturmgruppen pilots forced by tactical order to close to within 200 yards before firing. The D9 variant, the Dora 9, introduced in August 1944, was the technical answer to the Spitfire Mark 14 and P-51 Mustang. Tank replaced the BMW 801 with the Junkers Jumo 213A, a liquid-cooled 12-cylinder V engine. The Dora reached 686 kilometers per hour at 6,600 meters. The German pilots who flew it consistently described it as the best German propeller fighter of the entire war. Adolf Galland, after flying a Dora 9 in January 1945, declared that they finally had something to fight on equal terms against Allied adversaries. The problem was the same as always in those last months. There weren't enough Dora 9s, there wasn't enough fuel, there weren't enough trained pilots to blow it up. Approximately 20,000 FW-190s in all variants were produced between 1940 and 1945. The FW-19 Otoge was the only German fighter of the entire war to maintain the ability to surprise the Allies from its appearance in 1941 until its last day of combat. Captain Helmuth Wells, an infantry officer with the German 4th Regiment at Stalingrad, described in his 1959 memoirs what he called the war within the war. Each building was a position, each staircase a battlefield, each basement a fortress to be taken room by room with grenades and pistols. Conventional artillery was useless because buildings absorbed direct hits with an inertia that 75mm shells barely disturbed. What was needed, Wells wrote, was something that would turn a building to dust in one fell swoop. The Sturm Tiger was exactly that. Developed from the lessons of Stalingrad and urban fighting in Sicily in 1943, the Sturmörserwagen 606/4 answered a particular question that street combat had posed unanswered: how to destroy enemy positions heavily entrenched in masonry structures without exposing infantry to sniper fire, and without relying on field artillery that required fixed positions and slow response times. The Alket Company developed the vehicle throughout 1943 on the modified chassis of the Tiger I. The engine was moved to the center of the vehicle to create space for the main gun's loading system. That weapon was the 380mm RW-61, an adaptation of the Kriegsmarine's anti-submarine launchers that the Navy had developed to drop depth charges against submarines. The rocket shell weighed 330 kilograms, of which 125 were high explosive power. A direct hit on a 4-story masonry building was equivalent, according to tests carried out at Hillersleben in June 1943, to the simultaneous detonation of 300 hand bombs. The pressure wave collapsed adjacent structures that had not received the direct impact. The crater in open terrain was between 4 and 5 meters deep and 10 meters in diameter. Handling a 330-kilogram shell inside an armored vehicle was an engineering problem that the Sturm Tiger design elegantly solved. A 2.5-ton crane mounted on the rear deck, hydraulically operated from the inside, transferred shells from external supply vehicles to the breach without exposing the crew to outside fire. Inside the vehicle, a rail-mounted cargo cart moved the projectile from the storage racks to the chamber. The entire loading process took approximately 10 minutes, which set the maximum rate of fire at about 6 rounds per hour under ideal conditions. It was not a weapon of continuous suppression. It was a high-precision wrecker with slow reload and ultimate spin. The superstructure had 150mm frontal armor. The total weight reached 65 tons. The firing range of the RW61 was narrow, 0 to 85 degrees of elevation and 10 degrees on either side of the vehicle's centerline, and for targets outside that arc, it was necessary to move the entire Sturm Tiger. The first operational deployment was during the crushing of the Warsaw Uprising in August and September 1944. The Polish Armia Krajowa had turned Warsaw into a network of defensive positions, with tunnels under sewers, snipers in bell towers, and machine gun nests at every crossing. The Sturm Tigers of the 1st Sturmörser Company were used to systematically demolish the building blocks with the highest strength density. The tactical effect was definitive. There was no position that could withstand a direct hit from RW61. The cost to the Polish civilian population trapped in the surrounding buildings was catastrophic. Reports from SS Obergruppenführer Erich von Dembach-Zelewski, who commanded the operation, cited the Sturm Tiger as the most effective weapon for neutralizing the most solid urban points of resistance. Only 18 Sturm Tigers were ever produced, built at the Alket plant in Berlin-Spandau from Tiger 1 chassis recovered from combat and repaired. The meager figure reflects both the limits of German industry in 1944 and the recognition that it was a specialized weapon for a type of combat that Germany hoped it would not need. In October 1941, somewhere between Bryansk and Orel, a column of the German 4th Panzer Group encountered a concentration of Soviet T-34s that would not retreat. The Panzer IIIs opened fire at 600 meters. The shells bounced off the sloped armor of the T-34. The 50mm gun of the Panzer III, perfectly effective against the Soviet armor of previous years, lacked the power of penetration versus the geometry that Kharkov engineers had incorporated into the T-34. The sloped armor was not simply thicker. The slope meant that the shells tended to deflect rather than penetrate, multiplying the actual protection beyond what the nominal thickness indicated. General Heinz Guderian toured that front in November 1941 and described the experience in his report to the OKH in unambiguous terms. The Russians have a tank that we cannot match with current means. The Special Tank Commission that the OKH sent to the front that same month arrived with engineers from MAN, Daimler-Benz and Henschel with the explicit instruction to analyze the T-34 and recommend how to copy or surpass it. The Daimler-Benz team proposed a working copy of the T-34 with specific improvements in optics and communications, diesel engine and adapted suspension. It was quick to implement. Hitler, who personally oversaw armored developments with a micromanagement that made generals desperate, preferred Mann's proposal. Not an improved copy, but a vehicle that would incorporate the lessons of the T-34 and then surpass them in firepower and protection. The result was the Panzerkampfwagen 5 Panther. It incorporated armor sloped at 55 degrees in the front of the hull and turret, surpassing the protection of the T-34. He surpassed it in firepower with the KWK cannon 42 of 75mm L70, and it exceeded it in optics with the TZF-12A binocular sight, which allowed it to identify and hit targets at distances where the T-34 still fired by the commander's visual estimation. Production began in November 1942 at the MAN plant in Nuremberg. The baptism of fire at Kursk in Operation Citadel of July 5, 1943, was a technical catastrophe. Of the 200 Panthers of the 48th Panzer Corps deployed to the southern sector, about half experienced serious mechanical breakdowns in the first 48 hours. The Maybach HL230 engine overheated. The ZFAK 7-200 transmission, designed to transmit 700 horsepower through a chassis that now weighed 44 tons, failed under the accumulated stress of overnight transfers to starting positions. Fires in the engine compartment caused by faulty fuel connections in the first production batches, disabled dozens of vehicles without a single shell being fired. What followed was remarkable for its speed. Field engineers identified the faulty fuel connections in the first week of combat. Speer dispatched technical teams directly to the front. The modifications were incorporated into the production line. By the fall of 1943, the Panther Ausf A was significantly more reliable than the Ausf D, who had fought in Kursk, and the Ausf G, introduced in March 1944, was the most mechanically robust version of the entire series. The nearly 6,000 Panthers produced in total fought on all European fronts, from the steppes of Ukraine to Normandy and the Ardennes. The M4 Sherman, a workhorse of the US Army and its allies, could not penetrate the Panther's frontal armor at normal combat distances with the standard 75mm gun. The 76mm gun, introduced in the M4A3 76W variant, could achieve it at less than 400 meters, a distance at which the Sherman's crew rarely survived long enough to fire. General Omar Bradley acknowledged in his memoirs that this asymmetry was compensated for by the Allied numerical superiority, but not resolved. On the first day of the Ardennes offensive, December 16, 1944, in the northern sector of the attack, 3 Sherman tanks of the US 743rd Armored Battalion were destroyed in less than 40 seconds. None of its crews were able to identify the aggressor. The Jagd Panther that opened fire from the edge of the forest at 1,000 meters had fired 3 times with 11-second intervals between each detonation. Subsequent analysis of the destroyed armor revealed 94mm diameter perforations traversing 76mm of sloped armor. The first Allied intelligence report documenting the damage used the word incontestable. The Jagd Panther was the culmination of a philosophy that took years for the Wehrmacht to articulate coherently. Not a general-purpose tank capable of multiple roles, but a pure armor-destroying instrument, optimized for a single function, built on the best available chassis. The decision to mount the 88mm L71 Pak-A43 on the hull of the Panther was formally taken in October 1942, when the Heereswaffenamt accepted Daimler-Benz's proposal. The design eliminated the conventional tank's rotating turret to install a fixed, low-profile combat cockpit, with the gun poking out of a rut with 9 degrees of lateral travel and 15 degrees of elevation. To aim outside that narrow arc, it was necessary to move the entire vehicle, which required the driver and commander to coordinate on which lives depended. The compensation was total in firepower. The Pak-43 that armed the Jagd Panther was not the 88mm gun that had demolished British tanks in Tobruk or that of the Tiger I. It was a substantially longer evolution with a 6.3-meter tube generating a projectile velocity of 1,000 meters per second for the PSGR 39/43 armor-piercing ammunition. At that speed, at a distance of 1,000 meters, it pierced 190 millimeters of homogeneous armor. At 2,000 meters, where many enemy armored vehicles had not even yet located where the fire was coming from, it crossed 159 millimeters. The Soviet IS-2, with its 120mm frontal armor, could be destroyed from distances to which its own armament could not respond effectively. Production began in January 1944 at M1AG's Brunswick plant. Allied bombing raids repeatedly disrupted the pace of manufacturing. Despite this, 415 Jagd Panther were completed between January 1944 and the end of the war. On the Eastern Front, records of destruction documented by units such as the Schwere Panzerjäger Regiment 656 have been checked against Soviet loss records. Lieutenant Alexander Kurov, commander of an IS-2 of the 7th Guards Tank Corps, left in the Soviet archives a testimony describing low-silhouetted German vehicles opening fire from more than 2 kilometers before he could determine their exact position. The Jagd Panther was exactly the weapon Germany needed in 1943 to compensate for its growing numerical inferiority. He arrived in 1944 when that inferiority was already on a scale difficult to compensate for with tactical quality, no matter how exceptional it was. By the spring of 1944, Allied aviation had turned any movement of German columns in broad daylight into a high-risk operation. The RAF's Hawker Typhoon and the USAAF's P-47. Thunderbolt attacked at low altitude with rockets and autocannons that could destroy anything from a half-track to a Panther in a single pass. The Soviet Ilyushin Il-2 did the same on the Eastern Front, with a systematicity that panzer commanders later described as the factor that most conditioned the pace of their operations in 1944 and 1945. Existing German anti-aircraft systems did not solve the problem. The fixed-emplacement 88mm flaks were lethal to high-altitude bombers, but took hours to displace. The Flakpanzer IV Wirbelwind and Ostwind offered acceptable mobility, but their gunners fought exposed in open turrets under the same fire they intended to counter. The Flakpanzer Koalion was the most ambitious response to that requirement. Designed in 1944 on the Panther's chassis, deliberately chosen to ensure it could keep up with the fastest armored units, it mounted a fully enclosed turret with 30mm of armor that protected the crew against the main fatal failure of its predecessors. Inside the turret, two twin-mounted 37mm Flak 103/38 autocannons could fire 500 shells per minute at a combined rate, with an effective ceiling of 4,800 meters against aircraft at speeds below 600 kilometers per hour. The direction of fire incorporated an analog calculator to estimate the interception point of the projectile, based on the apparent speed and direction of the target. Firing at a moving plane is not the same as aiming directly at the plane. You have to calculate where the plane will be when the projectile reaches that altitude. The Koalion also added a stereoscopic rangefinder to measure distance more accurately than standard visual estimation systems, capabilities absent in the Wirbelwind and Ostwind. Two prototypes were built in the summer and autumn of 1944. The tests revealed a promising system with solvable technical problems. The synchronization of the rate of fire between the two guns and the ammunition feed system tended to fail under elevated temperatures. Engineers estimated that the fixes would require weeks of additional development, not months. The High Command opted to postpone production until these problems were resolved, continuing in the meantime with the Ostwind as an interim solution. By the time the Koalion's problems could have been solved, the Allied bombing raids on German industry had reduced production capacity to levels that made it impossible to add another complex vehicle to the manufacturing line. In the December 1944 Battle of the Bulge, low-altitude Allied air attacks on SS columns destroyed more vehicles than ground fire. The Ostwind did not prevent it. The Koalion wasn't there to try either. On August 9, 1944, in Normandy, Lieutenant Philippe Michard, commander of a Sherman Firefly of the Régiment Blindé Canadien de Montréal, recorded in his diary the most accurate and most disturbing description of the Tiger II in combat. 3 Fireflies against one of them. First shot at 400 meters, it bounced. Second shot closer, it bounced. The third was at 200 meters with an oblique angle on the rear side plate. That did penetrate, but we'd already lost 2 of the 3 tanks. It wasn't a battle, it was an execution in reverse order. The Tiger II, the Königsteiger, the king of the Tigers, was born from a decision in January 1943. Hitler, disturbed by early encounters with the Soviet IS-1 and aware that the 122mm IS-2 was under development, ordered the Heereswaffenamt to begin designing a successor to the Tiger I that would surpass anything the Soviets could field in 1944. The Henschel and Porsche companies submitted proposals. Henschel's, more conventional and mechanically more reliable, was selected. The Tiger II's armor was the reason for its existence. The front of the superstructure reached 150mm inclined at 50 degrees, equivalent in real ballistic protection to more than 230mm of vertical steel. The sides of the hull were 80mm. No Allied tank gun in service in 1944 could penetrate that frontal at normal combat ranges. Combat records document instances in which Tiger IIs received dozens of hits in the front without being penetrated, destroying enemy vehicles at distances where their targets could not respond effectively. The problem was the engine. The 700 horsepower Maybach HL230, designed for the 44-ton Panther, was now to move 69.4 tons of steel. The resulting specific power was 10.1 horsepower per ton, the lower limit of what is technically acceptable for a combat vehicle. The maximum speed on the road was 41.5 kilometers per hour, but in real field conditions, it rarely exceeded 30 kilometers per hour on a sustained basis. Fuel consumption was the other limiting factor. On the road, the Tiger II consumed between 550 and 700 liters per 100 kilometers. In the field, consumption could triple, with Allied aviation systematically attacking German refining facilities and fuel depots. Since the summer of 1944, many Tiger II-equipped units were receiving assignments covering less than half of their operational needs. The Ardennes showed the clearest end of that limitation. The Kampfgruppe Piper of the 1st SS Panzer Division advanced with Tiger II and Panther until it ran out of fuel in the Belgian region of La Glaise and abandoned its vehicles intact because there was no way to move them. The Tiger II was a fortress on land, but fortresses need supply lines. 489 Tiger IIs were produced between January 1944 and the end of the war. On the Western Front, it was the vehicle that Allied armor commanders feared the most, not because of its numbers, but because each encounter produced disproportionate losses until they learned to flank it, isolate it, and wait for mechanical problems or lack of fuel to do the job that shells could not do head-on. On May 13, 1940, on the outskirts of Dinant, General Erwin Rommel watched from his command SDKFZ 251/3 as the first units of the 7th Panzer Division crossed the Meuse River under fire. What made possible the coordination that Rommel supervised at the time was the communication system integrated into that vehicle, 3 different radios operating simultaneously. The 30-watt FUG-8 for communications with the divisional headquarters, the 20-watt FUG-7 for direct contact with close support aviation, the FUG-5 for local tactical communications with the vehicles of the sector itself. The Blitzkrieg wasn't just a tactical idea about speed and focus. It was, to a large extent, a communications engineering problem that the SDKFZ 251 solved. The Sonderkraftfahrzeug 251 was developed by Hanomag from 1938 as a standard transport vehicle for the Panzergrenadiere divisions, the mechanized infantry that was to operate in close coordination with the armor. The design adopted the half-track configuration, conventional front wheel steering for road handling, main traction and weight bearing via the rear track axle. This combination made it possible to cross terrain that made conventional trucks useless without reaching the weight and mechanical complexity of a completely tracked vehicle. The basic version, the SDKFZ 251/1, carried 9 infantrymen plus crew in a semi-open rear compartment with 14.5mm armor. Such armor was not sufficient against infantry gunfire at close ranges, but it effectively protected against fragments of artillery and shrapnel that in the most of the fighting posed the greatest danger to the infantry on the move. What made the SDKFZ 2511 one of the most influential vehicles of the war was the proliferation of specialized variants developed on the same platform. The 251/9, known as the Stummel, integrated a short 75mm howitzer for direct fire support to the landing infantry. The 251/16 carried 2 flamethrowers to dislodge entrenched positions in dense vegetation or structures. The 251/17 mounted the 20mm Flak 38 anti-aircraft gun on a turntable. The 251/20, developed in 1944 as part of the Sperber night combat system, carried a 600mm infrared projector that illuminated the battlefield with light invisible to the human eye, but detectable by the FG 1250 scopes installed on modified Panzers. In field tests during the autumn of 1944, the system allowed those panzers to detect targets at 200 meters in complete darkness. It was the first integrated night combat system in military history. Heinz Guderian, who had intellectually designed the Blitzkrieg as a doctrine, coordinated Panzergruppen operations from Type 251/3 vehicles during the fall of France in 1940. The speed with which decisions were transmitted and executed was inseparable from the speed with which the 251/3 allowed them to be communicated. Total production reached 15,252 units in all variants between 1939 and 1945, making it the most produced half-track of the war. The Allied armies captured SDKFZ 251s in quantity during the German retreat of 1944 and 1945. Its engineers came to conclusions that directly informed the development of the American M113 and the Soviet BTR-50 in the post-war period. In April 1945, soldiers of the United States Third Army entered the Gotha plant in Friedrichsroda and found something that none knew how to classify. It was not a conventional aircraft. It was a wing, a single surface of wood and steel with no fuselage or tail, with two engines buried inside and a cockpit integrated into the central curvature. The engineers of the technical intelligence team who analyzed it over the next few days sent Washington an assessment telegram with a single word: extraordinary. The Horten Ho 229 was born out of Reimar Horten's three-decade obsession with the pure flying wing. From the 1930s, Reimar and his brother Walter built gliders from Ho 1 to Ho 6 that demonstrated a central idea. Eliminating the fuselage and tail eliminated all parasitic aerodynamic drag from those elements, radically improving efficiency. A conventional aircraft carries with it the resistance of the fuselage, the empennage, the joints between surfaces. A pure flying wing has none of that. The Luftwaffe bureaucracy listened to the Hortens with continued skepticism for years, until the urgency of 1944 changed the rules. Goering issued the specification known as the 3x1000, an aircraft capable of carrying 1,000 kilograms of bombs at 1,000 kilometers per hour with a radius of action of 1,000 kilometers. No conventional design could meet it. The Hortens, yes, on paper. The Ho 229V1, the first glider prototype without an engine, flew in March 1944 and demonstrated manageable characteristics for such a radical configuration. The Ho 229V2, equipped with two Junkers Jumo 004B engines, made its maiden flight in December 1944. Test pilot Erwin Ziller reported speeds close to 800 kilometers per hour and an overall behavior that exceeded his expectations. In February 1945, Ziller was killed when one of the engines failed during a test and the plane crashed near Oranienburg. He was the most qualified pilot in the program. There was neither time nor person to replace him. What neither Ziller nor the Hortens explicitly documented in terms of stealth design was that the wing structure incorporated properties that made radar detection difficult. The structural core mixed pulverized carbon with adhesive, a compound that partially absorbed centimeter radar waves. The flat silhouette of the wing had an intrinsically reduced cross-section, and the engines buried inside, without external nacelles, did not generate the reflections that gave away conventional aircraft. Tests conducted by Northrop Grumman in 2008 with an aftershock confirmed that Ho 229 would have significantly reduced its detection in Allied radar systems of the time, especially at low altitude. In 1944, German engineers had no formal science of radar stealth, but they had come to similar conclusions from a completely different angle. Goering ordered mass production under the name Gotha Go 229, with 40 pre-production units planned. Nothing materialized. The V3, almost completed in Friedrichsroda, was the only survivor flown to the United States. Today, it is in the Udvar Hazy Center of the Smithsonian Institution in the process of restoration. It is the only physical example of a design philosophy that would take the world 40 years to formally rediscover. The principles of the reduced radar signature flying wing that B-2 Spirit engineers investigated decades later were the same ones that Reimar Horten had partially implemented in a hangar in wartime Germany. 69 days. That is the time that elapsed between the official approval of the He-162 program in September 1944 and the first flight of the prototype on December 6th of that year. No jet fighter aircraft has gone from specification to flight in comparable time, before or since. The Reich Ministry of Aviation had issued in September 1944 a specification that would have seemed impossible 2 years earlier. A jet fighter built mainly of wood and aluminum in leaf, pilotable by young people with minimal training and producible in massive numbers. Ernst Heinkel responded within 4 days with a near-circular fuselage design, with the BMW 003 engine mounted in a dorsal nacelle above the fuselage. An unusual configuration that avoided the complexity of integrating the engine into the interior and reduced the risk of fire in the event of engine failure. The wings of wooden construction, to preserve the strategic aluminum that was scarce, had moderate shaft. Standard armament was two 20mm MG 151/20 guns in the nose. Top speed, 840 km per hour at 6,000 meters, higher than the ME 262 at that altitude. Rate of climb, 23.5 meters per second, comparable to the best fighters of the immediate post-war period. The problems were serious and some directly lethal. The glue used on the wooden wings proved unstable under extreme temperature and humidity. In the first few months of operation, several instances of detachment of the leading edge of the wing in high-speed flight caused fatal accidents before emergency structural modifications solved the problem in subsequent production units. The BMW 003 was slow to respond to changes in acceleration below 300 km per hour, a critical condition during the approach to landing. Several pilots died when, in the go-around maneuver, when it is decided to abort a landing and get back on board, they increased the power too sharply and the plane responded with a violent and unrecoverable roll at low altitude. The Volksjäger program, the People's Fighter, envisaged that the He-162 would be flown by young Hitler Youth men with a few hours of glider instruction. Luftwaffe pilots and instructors rejected the idea with the firmness of those who knew that the He-162 required real dexterity to operate safely. 320 units were manufactured by the time the war ended, with 800 more in production at different plants. The main operational unit, I/JG-1, began equipping the aircraft in February 1945 and carried out a limited number of combat missions before the collapse of the front. The RAF intelligence teams that captured HE-162S intact at the airfields of northern Germany in May 1945 submitted their analyses urgently. The plane had real problems, but it also had obvious solutions. With 6 more months of development, it could have been a threat of a different nature. On September 8, 1944, at 6:43 p.m., an unannounced roar shook the Chiswick neighborhood of London. There was no alarm, no sound of engine approaching. The building simply exploded, killing 3 people and injuring 17. It was the first operational hit of a V-2, the first ballistic missile used as a weapon of war in history. It was reaching 5,580 kilometers per hour at the time of impact, well above the speed of sound. The explosion came before any sound that anything had been fired. The A4, the technical designation of the V2, was the result of years of work by Wernher von Braun and his team at the Peenemünde Research Center on the island of Usedom, where liquid propellant rocket experiments had begun in 1937. Under the supervision of General Walter Dornberger. The vehicle measured 14 meters and weighed 12.5 tons at launch, of which 8.8 were propellant, 3.9 tons of liquid oxygen and 3.96 tons of 75% ethyl alcohol. The engine burned that combination in 65 seconds, accelerating the missile from 0 to cut-off speed at 88 kilometers altitude. The warhead carried 910 kilograms of the explosive amatol. The probable circular error was 2 to 3 kilometers. It was not a weapon of surgical precision, but against a target the size of London or Antwerp, the inaccuracy was secondary to the effect of a threat that no one could intercept or predict. Production in the Nordhausen tunnels, the Mittelwerk dug into the mountain to protect it from Allied bombing, cost at least 12,000 lives among the prisoners of the Dora concentration camp who performed forced labor. More people died making the V2 than in the V2 bombing raids on Allied targets. Albert Speer repeatedly questioned the program's profitability. The V2 consumed more resources than any other German weapons project of the war, including the nuclear program. Between September 1944 and the end of March 1945, 3,172 operational V2s were launched. Approximately 1,054 hit the London area, causing some 2,700 deaths and more than 6,000 serious injuries. Another 1,600 fell on Antwerp. The effect on civilian morale was real, but not decisive in any strategic sense. What the V2 initiated transcends any measurement in terms of the 1944 to 1945 war. Von Braun and dozens of his engineers were transferred to the United States under Operation Paperclip. The Soviets captured Peenemünde and the Mittelwerk, transferred key engineers to the USSR, and used the A4 as the base for the R1 rocket, the point of origin of the line that would reach the R7, the missile that launched Sputnik in 1957. The American Redstone, Jupiter and Saturn V rockets are also direct descendants of the technical line that von Braun and Dornberger developed on a Baltic island between 1937 and 1944. And in July 1969, a rocket derived from those principles took the first humans to the moon. Before the American L-5TP-7 existed, before the Soviet BTR-50, before modern armies standardized the amphibious combat vehicle as a standard element of their battle orders, the Wehrmacht developed the Landwasserschlepper, built by Rheinmetall Borsig since 1935. It was the first heavy amphibious armored vehicle with self-traction operational in any army in the world. The name describes the function bluntly: amphibious land and water tractor. It was a tracked vehicle with a pontoon-shaped hull that provided it with inherent buoyancy, propelled in the water by a rear propeller driven by the same land engine. The transition between land and water locomotion was direct. The vehicle entered the water, activated the propeller propulsion and sailed. The 300-horsepower Maybach HL-120 engine provided 18 kilometers per hour on land and 12.5 in water. The 10 to 14.5 millimeter armor protected against small arms fire and shrapnel from light artillery. The main capacity was towing. He could drag a pontoon barge loaded with up to 20 tons, enough for a full Panzer III or IV or a heavy artillery piece with his tractor, across rivers of considerable width, with heavy vehicles that would otherwise have needed engineering bridges that took hours to build under enemy fire. Only 21 units were made, reflecting that it was a niche vehicle for specific river crossing scenarios. The Landwasserschlepper participated in the crossings of the Dnieper and other Soviet rivers during Operation Barbarossa in 1941, accelerating the pace of advance where conventional pontoons would have created traffic jams. They were explicitly considered for Operation Sea Lion, the planned landing in Britain that was never executed. In this hypothetical operation, they would have transported the first armored vehicles from the barges to the shore without the need for port facilities or firm sandy beaches. The principles that the vehicle validated, amphibious hull, dual land-to-water propulsion, heavy lift pulling capability, are the same ones that modern militaries adopted as standard decades later. The Wehrmacht had come before in too small numbers to matter operationally, but with a conceptual clarity that later developments would confirm. On the 24th of December 1943, at the Böblingen test site, 188 tons of steel rolled on its own tracks for the first time. It was the Panzerkampfwagen 8 Maus, the largest battle tank ever built. The name, Maus in German, was ironic in a way that Ferdinand Porsche, its creator, may not have quite calculated. Hitler had commissioned the project in 1942 with the instruction to create an absolutely impenetrable vehicle capable of breaking through any defensive position. Albert Speer, its armaments minister, received the news of the first shoot with the concern of someone who knew that the project consumed resources without an operational justification that the Maus could never provide. Armor was unprecedented in any ground vehicle: 200 millimeters on the front of the hull, 180 millimeters on the sides, 240 millimeters on the front of the turret. To put it in perspective, the Tiger II, the most heavily protected German heavy tank in active service, had 150 millimeters at the front of the superstructure. The Maus had a third more, with an additional tilt that multiplied the actual ballistic protection. No Allied tank or anti-tank gun in service in 1944 could penetrate that front at any practical combat distance. The weaponry was equally extreme. The 128mm L55 KWK-44 gun could destroy any Allied tank above 3,500 meters, accompanied by a 75mm coaxial gun for secondary targets. With the 1,080 horsepower Daimler-Benz MB509 engine, derived from an aviation engine, the specific power of the Maus was 6.4 horsepower per ton. Maximum speed on the road, 20 kilometers per hour. In clay soil or plowed fields, the vehicle sank under its own ground contact pressure before advancing significant distances. He could hardly cross any European bridges. To cross rivers, a procedure was designed where the Maus would advance along the river floor under a breathing snorkel, while another Maus on the opposite bank supplied it with electrical energy through a submerged cable to power the traction motors, an operation that required hours of technical preparation for each crossing. Speer cancelled mass production in 1944. 2 prototypes were built. When Soviet troops advanced on the Kummersdorf range in April 1945, German personnel deliberately destroyed both to prevent capture. The Soviets found the wreckage, combined the surviving parts of the 2 prototypes, and reconstructed an example that is now on display at the Kubinka Armored Museum near Moscow. The Soviet technical analysis was concisive: insufficient tactical mobility for any real operation, logistics impossible to sustain in the field, total vulnerability to aviation. Every ton of steel from the Maus was a ton that didn't make it to the Panthers and Jagdpanther that Germany did need and that the Allies feared to find. In 1942, when the Wehrmacht was still advancing on Stalingrad, engineer Heinrich Ernst Kniepkamp argued before the Heereswaffenamt that the German armoured system was about to collapse under the weight of its own complexity. Too many different platforms, too many incompatible spare parts between vehicles doing similar tasks, too many parallel manufacturing processes consuming scarce resources without producing economies of scale. A spare part for the Tiger I was useless on a Panther, which in turn did not share components with the Panzer IV. Each armoured division carried with it a multiplied logistics of spare parts. Kniepkamp's solution was a family of standardized chassis from which multiple combat vehicles could be derived, simplifying manufacturing, logistics, and field maintenance. It was a technically sound argument that came 2 years late on an industrial base that the Allied strategic bombing was methodically beginning to dismantle. The E-100 was the maximum class of that family, projected between 130 and 140 tons. Adlerwerke from Frankfurt received the commission. The result was a vehicle 10.27 meters long and 4.48 meters wide. The front of the hull reached 200 millimeters of armor. The turret, designed for the 128mm L55 KWK-44 gun, the same as the Maus, had 240 millimeters at the front. No Allied anti-tank weapon in service could penetrate that front. The peripheral track-bearing system that Kneepkamp designed to distribute the exceptional weight placed the wheels in an external position, simplifying field maintenance compared to the complex interleaved lattice of the Panther and Tiger II. The resulting width, however, exceeded most European bridges, which would have required specialized crossing engineering for almost any real strategic move. It was not a minor technical obstacle. In Western Europe, where rivers mark the great axes of advance and retreat, a vehicle that cannot cross a conventional bridge is not a tactical weapon but a fixed element, vulnerable to any flanking operation. The prototype was 40% complete when British troops from the 6th Commando Group found him at Haustenbeck, near Paderborn, in May 1945. The chassis and engine were installed, the turret and armament not. The Royal Armoured Corps engineers who inspected it calculated that the 700 horsepower Maybach HL230, identical to the 44-ton Panther, would generate a specific power of just 5 horsepower per ton to move 140 tons. The Panther had 16 horses per ton. The Tiger II had 10.1. The E100 would have had 5, half of the acceptable operating minimum. A transmission failure would have meant the immediate abandonment of the vehicle. No field recovery team could evacuate 140 tons with the means available in the frontline units. What Program E unwittingly demonstrated is that the rationalization Kneepkamp proposed would have been a real necessity since 1942, but it came when the industrial base could no longer respond. Hitler had rejected in 1942 and 1943 proposals for standardization that would have improved production into tens of thousands of lighter, more reliable, and easier to maintain vehicles, prioritizing instead extreme armor projects that captured his attention. Kneepkamp's good technical idea never had a chance to prove whether it would have worked at scale, buried under the very institutional mess it purported to solve. There are ideas that are too big to be discarded without analysis and too impossible to be taken seriously. The Landkreutzer P1000 Ratte, proposed in June 1942 by naval engineer Eduard Grotter to the Heereswaffenamt and personally overhauled by Hitler, occupied that territory for almost a year before Albert Speer cancelled it in 1943. No actual component was built. It existed as paper calculations, as preliminary models, and as conversations in the offices of the Ministry of Armaments. With a projected weight of 1,000 metric tons and dimensions of 35 meters in length, 14 meters in width, and 11 meters in height, the Ratte would have been the largest ground combat vehicle ever seriously proposed by any army in history. The main armament would consist of two 280mm SKC/34 guns, the same ones that armed the battleships Scharnhorst and Gneisenau, mounted on an adapted naval turret. As secondary armament, 128mm and 20mm guns and possibly 533mm torpedo tubes for use against vessels at river crossings. The propulsion required 8 MAN 512 engines of 2,000 horsepower each, for a total power of 16,000 horsepower, with a projected maximum speed of 40 kilometers per hour on the road. The required crew was estimated to be between 20 and 41 people, depending on the systems active simultaneously. The engineers who analyzed the project quickly identified the problems. The weight of 1,000 tons would generate a ground pressure that would sink the Ratte in any wet terrain before traveling a few kilometers. Crossing rivers was impossible without specialized engineering for several days. The European road and bridge network could not support its passage. And in contrast to Allied aviation, which in 1943 was establishing increasing superiority over Western Europe, a 35-meter vehicle at 40 kilometers per hour would be a target that could be destroyed by a bomber squadron on a single mission. Speer cancelled the project for precisely these reasons, in one of the few decisions of the German armaments program where technical rationality prevailed without notable political resistance. Between the Me-262 and the Ratte is the full arc of German armament from World War II. In that arc are the Panther, the V2, the HO-229, and the Coelian. Real projects, some of them extraordinarily advanced, all insufficient to reverse the course of a war that Germany was losing since Stalingrad, for reasons that no single weapon could solve. The deficit was not one of technical ingenuity. It was a time, of materials, of fuel, of trained pilots and crews, of industrial capacity, not subjected to systematic bombardment. The Ratte is not the story of a gun. It is the story of the limits of armaments thinking when it operates disconnected from operational reality, when engineering calculates what metal can sustain without asking whether soil can sustain it. Withstand metal if bridges allow passage, if fuel can arrive, if the enemy has aviation. The spectrum of German vehicles began with the Me-262, which existed and changed the history of aviation forever. It ended here, on paper, with a 1,000-ton land cruiser that never rolled. Between the two extremes lies the most complete story of what is possible when technical genius and strategic irrationality coexist in the same regime.